All right, this is section 10.3, part 2. Let's look at example 3. Example 3, we have parametric equations, x equals 2t minus pi sine of t, and y equals 2 minus pi cosine of t. And that's called a prolate cycloid, which we'll look at in a minute. Well, I'll go ahead and say, draw a sketch. I don't know if you have a sketch there or not, but anyway, the curve looks something like this. And it crosses itself right there at that point on the y-axis. And we're supposed to find the equations of the tangent lines at that point. So we'll have one that has a positive slope, and the other one, get a different color so you can see, the other one will have a negative slope. Okay, so we're looking for the equations of those two tangent lines, that one and the green one. All right, so the first thing we're going to have to figure out is where that crossing of itself occurs. And they tell us that it crosses when x is 0 crosses itself, they say, at 0, 2. So what we need to find out is, when does that happen? What is the t value then? So to find that out, we're going to set x equal to 0 and set y equal to 2. So, looking at the left-hand equation, algebraically to solve that is going to be a really tough call because it's partly polynomial and partly trigonometric. So, I'm going to go over here to the other equation, which only is trigonometric, and I think I can solve it for t. So, I'm going to subtract 2 from both sides, then divide both sides of the equation by the opposite of pi. And so 0 is equal to cosine of t. So when does that happen? When is cosine of t equal to 0? Well, that happens at pi over 2 plus pi n. So at pi over 2, 3 pi over 2, let me list a few of these. Pi over 2, 3 pi over 2, 5 pi over 2, etc. Infinitely many answers, and we can go backwards with negative n, and it's also when t is negative pi over 2, negative 3 pi over 2, and etc. towards negative infinity, and there are infinitely many of those. We're only interested in 2 of them, one where the curve is moving. By the way, the orientation of that curve, I forgot to say, is this way. So the first time it crosses through 0, 2 is where it's going to have the green tangent line. No, I'm sorry, the purple one. And the second time it'll be the green one. So there are only 2 times where it's at 0, 2. What we want to do is to figure out what time that could happen. I'm going to say, let's try things that are not too close, not too far from 0. So I'm tempted to try, for example, pi over 2, the smallest positive answer. So let's check that out. What is 2 times pi over 2 minus pi times sine of pi over 2? Well, 2 times pi over 2 is pi. Sine of pi over 2 is 1. Pi minus pi times 1 is 0. And that checks out. So that's a good one. So let's try the next positive one. 3 pi over 2. Let's see if that works out. So 2 times 3 pi over 2 minus pi times sine of 3 pi over 2 2 times 3 pi over 2 is 3 pi. Sine of 3 pi over 2 is negative 1. Negative pi times negative 1 is positive pi. So that's 4 pi, which is not 0. Okay? So let's go to some negative values, and maybe we'll find the other one there. Let's let t equal negative pi over 2. So 2 times negative pi over 2 minus pi times sine of negative pi over 2. 2 times negative pi over 2 is negative pi. Sine of negative pi over 2 is negative 1. Negative pi times negative 1 is positive pi, and the sum of negative pi plus pi is 0. That checks out. And we have our two answers. When t equals pi over 2 and when t equals negative pi over 2. Those are the two times where the curve is crossing through the point 0, 2. So, now what? Well, let's look at the question again. It's supposed to be the equation of those tangent lines at that point. Well, to get the equation of a line, not only do we need to know the point, which is 0, 2, we were given, we need to know the slope. Because if we know the slope, we can find the equation of a line using the point slope formula. Y minus y sub 1 equals m times x minus x sub 1. So the only missing component now is, well, what's the slope at those two places? So to find the slope, we're going to have to find dy dx. So x is way up there, so I'm going to write it down again. X was 2t minus pi sine of t. And y was 2 minus pi cosine t. So dx dt is 2 minus pi cosine t, and dy dt is negative pi times negative sine of t, so positive pi sine of t. So dy dx, therefore, is pi sine of t dy dt over 2 minus pi cosine of t. That is dx dt. Okay, so one of the lines, the slope will be calculated by taking dy dx and evaluating it at one of our two values. Let's do pi over 2 first. And then we'll do negative pi over 2 in a second. So we're evaluating the first derivative when t is pi over 2. So that'll be pi sine of pi over 2 divided by 2 minus pi cosine of pi over 2. Sine of pi over 2 is 1. 1 times pi is pi. Divided by cosine of pi over 2 is 0. 2 minus pi times 0 is 2. And so our point again was 0, 2. And at that point, our slope is positive pi over 2. So it's going to be y minus 2, the y-coordinate of our point, equals the slope, pi over 2, times x minus 0, or just x. And that's one of our tangent line equations. In fact, that one with the positive slope was the one that was up there in green, I believe. Yep, that's the one in green. Okay, now for the other line, we're going to calculate the slope using dy dx again. But this time it's going to be at time equals negative pi over 2. So doing the substitution, that will be pi sine of negative pi over 2 divided by 2 minus pi cosine of negative pi over 2. Sine of negative pi over 2 is negative 1. Pi times negative 1 is the opposite of pi. And cosine of negative pi over 2 is 0. 2 minus pi times 0 is 2. And so that slope is negative pi over 2, and that's the other one. I think that one was in purple. And using the point 0, 2, the equation of the tangent line will be y minus 2 equals negative pi over 2 times x minus 0. If you want to, you can add 2 to both sides if you just feel like you have to solve for y. For me, you do not need to do so. Leaving it in this point slope form is perfectly legitimate, and I'll take it. Okay, so let's see. What's next? The next thing I want to talk about is if a circle rolls along a line, then a point on its circumference will trace a path called a cycloid. If the circle rolls around the circumference of another circle, the path of the point is an epicycloid. Okay, so example 4. And I hope I gave you that picture because I'll rely on it pretty well. I won't be able to draw that as well as they can. If you recall, we talked about the cycloid earlier, and its graph looked sort of like this. This was the gum on the tire problem. Oops, that was supposed to look just like the other one. Oh, that doesn't look very good. Let me try again. Oh, I just can't draw that today. Oh well, I'll leave it. So that's the cycloid, and we dealt with that earlier. Now, if you have a circle, and the other circle is going around that, kind of thinking like this is Earth. Of course, the scale's all wrong. And then you have a circle traveling around on the circle. Then if you pick up a piece of gum here, for example, and the circle at that point is like right there, and you have the little circle rolling along the outside of the bigger circle, then the path it takes will look something like this. So it's kind of the same shape, but along the circle's circumference instead of along the line. And again, please, please, please look at the picture in figure 10.33. It's way better than this picture could possibly be. All right, so let's say that the little circle has radius 1, and the bigger circle has radius 4. And the big circle is centered at the origin. Okay, so if that's true, then the epicycloid, that curve that I tried to draw in pink there, will have this equation. X equals 5 cosine t minus cosine of 5t. And y will be 5 sine of t minus sine of 5t. Can you imagine trying to solve this for x or y in terms of x, or x in terms of y, eliminating the parameter? I don't think you could do it. And if you look at the curve, you've never seen anything like that epicycloid graphed with y equals a function of x or x equals a function of y. This is like totally new territory. So really the only good way to express this curve is parametrically. And so obviously it has a use. Now what we're supposed to do is find the distance traveled by the point, like the piece of gum that's on there, as it completes one trip about the larger circle. So I think the best way to do this would stay in quadrant 1, find the distance, the arc length of the epicycloid for just quadrant 1, and then multiply that by 4. Because at those points where it's not smooth at the x and y axes, both positive and negative, we're not going to be able to go over that anyway, because it's not a smooth curve there. So we can only find each quarter independently and add them up. Well, I'm going to use the fact that there's symmetry, and the distance traveled along this curve right here in quadrant 1 is repeated over and over and over and over again. So if I find that, I can multiply that arc length by 4. So we're going to find the arc length in quadrant 1 and multiply it by 4. Okay, so, oops, that was a little random mark there. Wow, what happened? That's weird. I can't make it go away. Oh well. Try to, if you can, ignore that little weird thing that's coming down from my H. Okay, so we're going to need to do, therefore, the arc length formula, which means we're going to need to know dx dt and dy dt. So I think I'll start with that. So the derivative of 5 cosine t is negative 5 sine of t. And then the derivative of cosine is negative, times the minus in front will make it positive, sine of 5t, and then the chain rule comes into effect, times the derivative of the inside function. The derivative of 5t is 5. Okay, so dy dt will be 5 cosine of t minus 5 sine, 5 cosine of 5t. Again, the chain rule comes into effect with that. All right, so the arc length is the integral from something to something. I'll come back to that. Of the square root of dx dt squared plus dy dt squared dt. Okay, now to find the places where the first quadrant stuff starts and stops, we're going to need to think about what t value would get us the point where we're starting, namely this point right here, where x is 4 and y is 0. That point is at 4, 0. So I'm going to guess, and I think I'm going to be happy with this guess. If t is 0, isn't 5 sine of 0 minus sine of 5 times 0 0? Let's check the other part, x. Cosine of 0 is 1. That'll be 5 times 1 minus cosine of 0 will be 1. 5 times 1 minus 1 is 4. Yep, that's good. So that's one of them. And I'm going to jump out on a limb here and say I think it might be where t is pi over 2. I do need to sort of check that out. If I'm wrong, I'll have to try something else. But I'm just hoping. Cosine of pi over 2 is 0. 5 times 0 minus 0 is 0. Oh, and by the way, the coordinates of that point right here are 0, 4. So I'm trying to get 0 for x and 4 for y. And pi over 2 gets 0 for x. That's good. And then 5 times sine of pi over 2 is 1. Sine of 5 pi over 2 is also 1. So 5 minus 1 is 4. Yep, that works. We get 0, 4. So the lower bound is 0. The upper bound is pi over 2. Okay, so I lucked out. That's good. Okay, so let's do the squaring under the radical. So that's going to be 25 sine squared t minus 50 sine of t sine of 5t plus 25 sine squared of 5t. I have enough room. Plus, let's put that in parentheses, kind of make it clear where that came from. And squaring the second one, I'll get 25 cosine squared t minus 50 cosine t cosine of 5t plus 25 cosine squared of 5t, and then dt. Okay. Whew. Boy, what a mess. Let's see what we can do. Well, one thing I noticed is I have 25 sine squared of t plus 25 cosine squared of t. If I were to factor out the 25, that would leave 25 times the quantity sine squared t plus cosine squared t. And I know the Pythagorean identity for sine squared t plus cosine squared t is that's equal to 1. So I have 25 times 1. So in other words, 25. The same thing will happen with 25 sine squared t plus 25 cosine squared 5t. 25 is a common factor. Factor it out. You're left with sine squared of 5t plus cosine squared of 5t, which is 1. 25 times 1 is another 25. All right. Then, let me see. I need to make this a little bit longer, I think. Then for these two, they have a common factor of -50. So let me pull that out. Sine t sine of 5t plus cosine t cosine of 5t dt. Okay. Now let's see, is there an identity that we can use here? I'm looking at the last part of that. 25 plus 25, of course, is not 25, is 50. Minus 50 times. Is there a trig identity where you have a sine of A, sine of B, plus cosine A, cosine B? Well, that may not be the order you're used to seeing it in, so let me remind you of what you're more used to. If I had cosine A, cosine B, plus sine A, sine B, what's the identity for that? Do you remember? That was the cosine of the first one, A, first angle, change the sign minus the second angle. This is the difference formula for cosine, is what that is. So I'm going to rewrite this as the cosine of A, the first angle, which is t, minus B, the second angle, which is 5t. Okay, dt. Alrighty. So let's see, the 50 is a common factor. So let me take that out, leaving 1 minus cosine of -4t. And I'm going to use another identity here. If I have a negative angle, is cosine even or odd? Since it's even, that'll give me back cosine of A. This is the even-odd identities. I think I mentioned at least once before in this class that everything you ever learned in a prior course could come up again, like these two identities. So you've got to know them. So the t minus 5t is -4t, and because of the even-odd identity, I can write that as +4t. And then there's another identity that I want to remind you of. The sine squared of an angle. This is the power reducing formula. The sine squared of an angle is 1 minus cosine of double that angle all over 2. So if I were to multiply both sides of that by 2, I would get 2 sine squared theta equals 1 minus cosine of 2 theta. So if you look at the angle on the right, 2 theta, and the angle on the left, theta, if you have an expression like 1 minus cosine of 4t, the angle on the other side is going to be half of that. Half of 2 theta gives me theta. So over here, this will be 2 sine squared of half of 4t, which is 2t. And so I'm going to use that identity. Oh, and by the way, that square root of something times something, you can rewrite that as the square root of 50, which is a constant I can pull out in front, times the square root of the other thing, and the other thing is replaceable with 2 sine squared of 2t dt. The square root of 50 is 5 square roots of 2. The 2 in front of sine squared 2t, if I split that into 2 radicals, will become square root of 2, which I'll pull out in front, leaving me the square root of sine squared 2t, which is sine of 2t dt. Okay, and so 5 times square root of 2 times square root of 2 is 5 times 2 is 10. The antiderivative of sine of something, kx, it was what we said before, is negative 1 over k cosine of kx. Of course, this is a t, don't forget that. Evaluated from 0 to pi over 2. Okay, so that's negative 5 cosine of 2 times pi over 2 is pi, minus negative, so plus 5 cosine of 2 times 0 is 0. So cosine of pi is negative 1. Negative 5 times negative 1 is 5. Cosine of 0 is 1. 5 times 1 is 5. And so that's 10. And the one thing I forgot to do all the way through this is that was the arc length for the first first quadrant only. And what I forgot to do is to multiply by 4. So I'm going to go back and squeeze that in and multiply the single version from 0 to pi over 2 by 4 to get the entire length. So this is good that I look back at my picture because I had forgotten that I needed to multiply by 4. So you obviously don't want that to be something you forget to do. Of course, at some point I would have had I remembered the 4 earlier, I would have multiplied 4 times the constants that are already there way earlier, but that's okay. So our final answer is 40. All right. So let's see what's next. Let's look at the next example. Let C be the arc of the circle x squared plus y squared equals 9. So that's a circle of radius 3 centered at the origin. So this circle. Okay, C is going to be the arc of the circle from 3, 0. So from 3, 0 to 3 halves, which is a positive number, 1.5. 3 square roots of 3 over 2, which is a positive number. So I'm going to say it's about right there. So this is the part of the curve that we're interested in. That pink one is C. Find the area of the surface formed by revolving C about the x-axis. Okay, so if you look at figure 10.34, I think I did copy that in there. You'll see a pretty good picture of what that's going to look like. I'm not going to even try to draw it because I'm sure I would mess it up. but it's a surface and the area of the surface. So to do this, we could try to find the equation of this for y equals a function of x and do it like we've always done it before. But what I'd like for us to try to do here is to represent this parametrically. So let me just try something and see if this works. To get the radius to be 3, I'm going to have x equals 3 times something, and I want it 0 for that to be 1. So I know cosine of 0 is 1, so that's going to be good. And if I went all the way to 0, 3, I'd want the y value at pi over 2 to be 3, and 3 times the what function of 0 will give me 1 at pi over 2? Well, that's going to be sine. So I think that will work. Now, how am I going to get it to stop at that point? Because I need to know the time value when that occurs. So it starts at 3, 0. So x equals 3 and y equals 0. And when is that true? Well, 3 is equal to 3 cosine t when cosine of t is 1. So that means t is 0. And we need to get the same thing over here. This over here is kind of like a double check. So dividing both sides by 3, I get 0 equals sine of t. And what angle, when you take the sine of it, you get 0? Well, the answer, of course, is, or one of the answers is 0. So we're going to start at 0. Oops, I shouldn't have written that yet, because the surface area formula has that 2 pi radius that we need to think about. So I will come back to the radius part of this in just a second. I'm working on the bounds. Okay, and if I want it to stop at x equals 3 halves and y equals 3 squareds of 3 over 2, that means that 3 halves will be equal to 3 cosine t, and 3 squareds of 3 over 2 will be equal to 3 sine of t. So if I divide both sides of both equations by 3, I get cosine of t equals 1/2, and sine of t equals square root of 3 over 2. And what angle is it that does both of those at the same time? Right, it's pi over 3. So that's the upper bound, pi over 3. Okay, now we need the radius function. So the radius function, since we're revolving about the x-axis, the radius is going to be measured from the axis of revolution to the curve. And of course, that's a measure of y. So the radius will be the y. The radius function will be y, which is 3 sine of t. So this is 3 sine of t times the square root of, and I did it again. Ordinarily I want to find the derivatives of x and y almost immediately and put it right underneath the x and y statements. So I'm going to kind of write this upside down. Let's find dx dt up here. That's going to be negative 3 sine of t, and dy dt is 3 cosine of t. So this should be dx dt negative 3 sine of t squared plus dy dt 3 cosine of t squared dt. So I'm going to pull that 3 out. That's going to make it 6 pi times the integral from 0 to pi over 3 of sine of t times the square root of 9 sine squared t plus 9, whoops, not supposed to write 3 when you say 9, Mr. Ford, don't mess that up, 9 cosine squared t dt. Alright, so you can factor out the 9, and the square root of 9 will be 3, which I'm going to pull out in front, so that'll become 18 pi. And what's left under the radical is going to be sine squared t plus cosine squared t, which is 1, and the square root of 1 is 1. So that whole radical expression simplifies to be 3, which I've already pulled out. Then the antiderivative will be negative cosine of t, evaluated from 0 to pi over 3. So that's negative 18 pi cosine of pi over 3 minus negative 18 pi cosine of 0. Okay, so cosine of pi over 3 is 1/2. 1/2 times negative 18 pi is negative 9 pi. Cosine of 0 is 1. 1 times 18 pi is 18 pi. And so my final answer is 9 pi. Okay, that's the end of this lesson. I will see you in class.